Hello and welcome back to math class. Today, vector and parametric equations of a plane. Planes are flat surfaces that extend infinitely in all directions. Everyday examples of plane segments could include a desktop, a floor, a whiteboard. Planes are represented on diagrams using a parallelogram denoted with the Greek letter pi. And I think it's probably because P for plane, P for pi. Each diagram that I'm about to show you shows sufficient conditions to uniquely define a plane. For example, if there's a line and an external point, the point's not on the line, there's only one plane that contains these two, and so the line and the point uniquely define a plane. If we have 3 points that are non-collinear, not lined up, anywhere in 3 space, then those 3 points define a plane. And you can reason this because we could develop vectors here, AB and AC, and together they make the linear combinations that would span this plane. 2 intersecting lines also define a plane. Anytime there's 2 lines that intersect in 3 space, no matter how they're oriented, if they meet, then there's only one plane that contains those 2 lines. A pair of parallel lines, like railroad tracks. If they're parallel, there's only one plane that contains them both. This brings up an interesting point. Are there any other kinds of lines besides intersecting lines and parallel lines? Well, in 3 space there is. It is possible for 2 lines to be neither parallel nor intersecting. An example of this would be if you were looking down from high up and you could see 2 planes, one going in one direction, one going in another direction, so they're not parallel, but they don't collide because one of them is at a different altitude than the other one. So while they are going in different directions, they never collide because they're on different altitudes. Recall lesson 6.8 from 2 chapters ago. It was about spanning sets. A spanning set for a plane is a set of 2 vectors such that every vector in the plane can be expressed as a linear combination of the spanning set. And the spanning set is often a basis, and the standard basis for R cross R was the vectors I and J. Now there's an infinite number of spanning sets for any given plane. For example, any 2 non-collinear, non-zero vectors will span the plane R cross R, or any plane. Here's an example. Okay, well this is the general case, really. State the vector and parametric equations of the plane that contains a given point and that is spanned by the given position vectors A, A1, A2, A3, and B, B1, B2, B3. Solution. The concept is the same as finding the vector equation of a line. For the line, we went to the line and then any multiple of its direction vector. So we would span the line. So what we'll do here is we'll go to the plane and then we'll span the plane using our spanning set here, A and B, because they're non-collinear. And so the idea is we go to the plane and then a linear combination of the spanning set, where T and S are any real numbers. So going to the point that we know is on the plane, this will do that, and then TA plus SB gives us our linear combination of the spanning set. And from this is derived the parametric equations x will always be x naught plus some multiple of a1 plus some multiple of b1. Y will be y naught plus ta1, ta2 plus sb2, because y is the second coordinate. Z will be the z naught coordinate plus t times a3 plus s times b3, because that's the third coordinate. Vector and parametric equations of a plane. Example, find the vector and parametric equations for the plane that contains 3 points. Now this is an example where the sufficient conditions is the 3 non-collinear points. And the solution is, use the 3 points to develop 2 direction vectors. So direction vector 1, use any 2 points. How about AB? AB is, we know how to do this, subtract backwards here. 8 minus 3, negative 4 subtract negative 2, negative 3 subtract 5, and this is a vector in the plane. And we just choose any other 2 points for a second direction vector. How about AC? So AC would be, again, subtract backwards. Negative 4 subtract 3, 5 subtract negative 2, and negative 1 subtract 5. And we have our 2 vectors that are in the plane that came from the 3 points. And now we'll set up our vector equation of the plane. And the vector of the equation of the plane will have 2 parameters. A, B, or C could be used for our P naught, so you have 3 points to choose from here. And so answers may vary. One possible vector equation is, I picked A. 3 minus 2, 5, plus t times one of those direction vectors plus s times the other one of those 2 direction vectors. So we've got 2 parameters involved now. And the parametric equations come straight out of the vector equations. X will be 3 plus 5t minus 7s. Y will be negative 2 minus 2t plus 7s. Z will be 5 minus 8t minus 6s. Example, check to see if either of these points, P and Q, is on the given plane. To check one point, well, let's start with P. Let's check P. Sub in 2 coordinates, which will yield values for 2 parameters, and then check the third coordinate for consistency. That will determine if point P is on this plane. So to check point P, sub in 44 and minus 31. Well, 44, if it's on the plane, is going to be equal to 3 plus 5t minus 7s. And tidying this up a bit. And then now minus 31, well, if minus 31 is on this plane, it's y. So it will equal negative 2 minus 2t plus 7s. And tidying that up a bit. So we have 2 equations and 2 unknowns. And I think you know what to do. Just carried it all forward here. There's our 2 equations and 2 unknowns. I put one on top of the other. And a quick review of elimination. Number over number, equals over equals, t terms over t terms, s terms over s terms. And since this coefficient here matches, except for the sign, we'll draw a line and make them eliminate by addition. So when we add the 7s's vaporize and disappear. And we get 12 equals 3t, and we know what t is. T is 4. And plugging 4 back in, I didn't show the work. 5 times 4 is 20, and drag it over here. You've got 21 divided by minus 7. So s will be minus 3. Now what? Well, the t equals 4 and s equals minus 3 satisfies our x and our y. How about, let's see if it satisfies our z coordinate. Test. Z equals minus 9 using these parameters. So if it works, then minus 9 will have to equal 5 minus 8t minus 6s. If it works. We don't know if it does. That's why we separate the sides. The left side of our equation is minus 9, and the right side is 5 minus 8 times t, which is 4, minus 6 times s, which is minus 3. Doing the math, we get 5 minus 32 plus 18, which is minus 9. And from this we conclude that the left side, which was minus 9, equals the right side, which is minus 9, and it follows, therefore, that it worked. And so P is on the plane, but Q cannot be. It's not possible that Q is on the plane because we worked already with 44 and minus 31. The parameters are like this. It has to be minus 9. So we can reach this conclusion. Another example, a plane P, pi, has, now this stands for all the position vectors. It could be x, y, z. And it's defined for you with a given point and given direction vectors. Determine the point of intersection between pi and the y-axis. So in other words, what's the y-intercept of the plane? If you can picture a plane in 3 space that slices through the y-axis. It would only do so at one point, wouldn't it? Solution. At any axis intercept in r cross r, or in r cross r cross r, the other coordinates are equal to 0. So our x-coordinate will equal 0, and our y-coordinate will equal 0. I'm sorry, our z-coordinate will equal 0, because we want the y-intercept. Now if the x-coordinate is 0, then 9 plus 3s minus 2t equals 0. And if our z-coordinate equals 0, then negative 1 minus 5s minus 4t will equal 0. And here we go again with the elimination. I multiplied x through by 2 to get 18 plus 6s minus 4t equals 0. Left the other one alone, drew a line, and since these match, we'll subtract. 18 subtract negative 1. 6 subtract negative 5. And we have that. The t is eliminated. Solving for s, and I strongly recommend fractions. Oh, sure, you could turn it into a decimal, that's true. And if we take our fraction and sub it into either one of the original equations, we get 9 plus 3 times s minus 2 times an unknown t equals 0. And this leads us to t equals 21 over 11. And I'm taking for granted that you can solve an equation that involves fractions. I'd suggest that you actually do it. And so we have an s, we have a t, and what was the question again? Determine the point of intersection between this plane and the y-axis. So we'll go to the y-coordinate and say, well, this y-coordinate will be 4 minus 7s plus t. Okay. 4 minus 7s plus t, and we'll sub in our s and t. And I would recommend that you do this math. It's good for your mentality. Do the math, and you end up with y equals 18. I recommend that you actually do this math in your head. Try it, it's good for you. Therefore, the y-intercept is 18, and that would be its coordinates, 0, 18, 0.